Everyone, and welcome to today's webinar, High-Resolution EELS on High-Entropy Perovskite Oxide Thin Films. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speakers at the end of the presentation. If we don't get to your question, we will follow up via email after the webinar. Now I'd like to introduce the speakers for today's webinar. Dr. Aladdin Ulrich is the coordinator of the Electron Microscopy Center and head of the Transmission Electron Microscopy Labs at the University of Augsburg. Since 2019, he has served as the chair of the Experimental Physics 4 at the University of Augsburg. Dr. Ulrich earned a degree in physics from the university in 2008 and later completed his PhD in 2013. From 2013 to 2019, he was a scientist and chair of the Experimental Physics 2 at the university. His research focused on transition metal oxide nanoparticles, synthesis, and physical properties. In 2025, he completed his habilitation at the University of Augsburg to earn his Privatscient. His thesis was on synthesis, structure, and magnetism of iron oxide nanoparticles. Our second speaker is Maximilian Mim. He's a PhD student at the University of Augsburg working on thin film oxides prepared by pulsed laser deposition with a focus on structural and magnetic properties. In 2022, he received a Master of Science degree in physics from the university. Maximilian completed his Bachelor of Science in Material Science at Augsburg in 2020. Now over to Maximilian.
Thank you for the kind introduction, and welcome everybody also from my side. Today, Aladdin and me, we will talk about the high-resolution EELS and high-entropy perovskite thin films. So the outline for today is the following. We start with first we start with a motivation. Why are high-entropy materials of interest? And then we come to the thin film preparation and also the structure analysis. This is covered by me. And the second part of our talk, the analytic TM, so EDS versus EELS, the thickness of a sample, why the thickness is important, also how we can measure the thickness by EELS, and also the elemental maps we obtain from EELS measurements will be covered by Aladdin. So let's get started with the first timeline, I would say. So back in 2004, the high entropy concept started with high entropy alloys. These two people, Cantor and Yi, brought the high entropy concept to the alloys. Then only 1 year later, the high entropy nitrides were first synthesized. Then 10 years later, the first high entropy oxide was synthesized by Roth. And in 2016, already high entropy diborides were synthesized. And in 2017, high entropy fluorides. Then 2018 was a big year for the high entropy concept because the high entropy perovskite oxides were first synthesized. And in the same year, also high entropy carburides and high entropy sulfides were synthesized. Then in 2019, high entropy silicides, in 2020, high entropy phosphides, and in 2021, high entropy carbonides were first synthesized as high entropy material. So what we can see is that a lot of material classes have been synthesized as high entropy material. So what is the definition of a high entropy material? So a high entropy material is a material with minimum 5 different elements in equiatomic ratio, which leads to an entropy of equal or greater than 1.61 times the gas constant. And also the material should be single phase. So how can we calculate the entropy? We're just using this formula. N is our number of elements and X is our atomic ratio. And what we see is that we have 5 or more elements, we are in the high entropy region. If we have between 2 or 4 elements in our material, then we are in the medium entropy region. And if we only have 1 element, then we're just in the low entropy region. And there's another material class which is connected to the high entropy system or high entropy. It's the stabilized entropy materials. So what is the entropy stabilized material? An entropy stabilized material is a material where the enthalpy where the entropy dominates the enthalpy term and is critical in the formation of the of a crystalline phase, and also there are some materials which does not exist in this crystal structure. So let's have two quick examples. So first we have here a rock salt, a high entropy rock salt. So 3 out of the 5 parent materials are rock salts, but copper oxide and zinc oxide have different structures. The same here for this high entropy perovskite, which is orthorhombic. 4 out of the 5 materials are also orthorhombic systems, but the yttrium manganese oxide is in a hexagonal system. So what we see is that the entropy forces some materials in different structures. So what we want is, here we have the Gibbs free energy equation, we have the enthalpy term and the entropy term. And what we want is, we want to minimize our Gibbs free energy. And we can do this if our entropy term, the T times S, is greater or bigger than our enthalpy term. So we have our enthalpy and our entropy. The enthalpy is temperature independent and defines our ground state. And the entropy depends on the number of elements and also on the equiatomic ratio, as we have seen before from the formula. And what now can be done if a material maybe has multiple phases at lower temperatures, that means that the enthalpy term dominates our entropy term. And if we increase the synthesized temperature, we can get to a single phase material, because then our entropy term dominates our enthalpy term. So how are these names connected? So we can connect it the following way. We have compositional complex materials. These are just materials with many elements inside, or different elements. A part of compositional complex materials are the high entropy materials, and also a small part of the high entropy materials are entropy stabilized materials. But what we also can have is, so if we have a material with a low entropy and is not entropy stabilized, we can call it a solid solution. But if we have a material which has a high entropy and is not entropy stabilized, we have a high entropy solid solution or a high entropy material. But then on the other side, we can have a material with low entropy, but which is entropy stabilized. But we can also have a high entropy material which is entropy stabilized. And why are high entropy materials of interest? Because they showed interesting properties. So they were investigated because of their thermoelectric effect, or because of water electrolysis, and also the magnetic or the electronic properties are of interest. And also they were investigated for the luminescence properties. And as in the title, we used a thin film. So how do we prepare thin films, or why are thin films of interest? Because most of the high entropy perovskites have been synthesized as bulk. And what we know is that thin films can have different properties compared to bulk system. And also the epitaxial growth is important because with the right substrate, we can control the orientation of our higher entropy film, and also properties can differ along different crystallographic orientations. So we prepare our thin film with pulsed laser deposition, also with PLD. So we hit a laser on a target which has our structure, which is directly our high entropy material, because PLD is a stoichiometric process. So everything what's in the target in the ratio should also be in our thin film. And why is this high entropy manganese perovskite of interest? Because it only has been synthesized as bulk yet, back in 2018 by Saka. And as substrate, we use just a common one like STO001. So, but why are manganese-based perovskite of interest? So they showed a lot of interesting properties. So some of them showed the metal to insulator transition. Others showed the magnetocaloric effect. Some others were investigated because of the charge, spin, and orbital ordering. And also others because of the colossal magnetoresistance. There's just few examples of the properties of these manganese-based perovskites. But how can we influence these properties, or what influences the properties? So we can influence these properties, or the Jahn-Teller effect influences our magnetic and electronic properties. Then also the tolerance factor, we can tune it. We can tune the properties by the tolerance factor. So if we use elements on the A side with different radii, our perovskite gets more or less distorted, which also has a direct influence on our magnetic properties. And then also the oxidation state. So if we have more Mn3 plus or Mn4 plus, or if we only have Mn3 plus, then we have a super exchange. Or if we have Mn3 plus and Mn4 plus, we have a double exchange. So with adding or changing elements on the A side, we have a direct influence on the MnO6 octahedron of our perovskite, which then influences our properties, especially the electronic and magnetic properties. So let's come to some results. So here you can see our XRD pattern obtained from the thin film, from the prepared thin film. Blue is our STO substrate. In yellow, it's an additional phase which we obtained. And in red, you can see our thin film. So here I wrote down the 002 and 110 orientation of the orthorhombics thin film because these are theoretically less than 1 degree apart. And just from XRD, from this graph, it's hard to say which orientation we have. So that we can, and we further investigated this. So we did a reciprocal space mapping, and what we then get from the reciprocal space card and with simulations, we saw that we have 3 different crystal orientations. So we have the 001 out of plane and 2 different 110 out of plane orientations, which are in plane rotated by 90 degrees. This was then confirmed by some electron backscatter diffraction measurements, so by EBSD. And what we can see is that here our structure, in the middle of our orthorhombic structure, we have cubes. And these cubes fit perfectly in different orientations on our cubic substrate. And then we were interested in the properties on atomic scale. So we prepared a lamella by focused ion beam. So this you can see here, just an overview. On the bottom, a little bit darker, is our STO substrate, and on top is our thin film. So let's have a closer look on our thin film. So what we can see is we have rows with brighter dots and darker dots. So, and also they are shifted half a unit cell. So from the set contrast, we can say, okay, the darker dots are manganese and the brighter dots are rare earth elements. And then what you also can see is that these rare earth elements are not on a straight line. So maybe you can see it here, they are not on a straight line. And also from the theoretical structure, which you can see on the left side, they shouldn't be on the left side, so shouldn't be on a straight line. And this is the orthorhombic distortion, which was really nice to see also in the TM image. And with that, I finished my part, and I will hand over to Aladdin now.
Thank you, Max. So welcome also from my side to this webinar. So let's begin first with a short repetition of the scanning mode of a transmission electron microscope. So when you're doing a STEM in such a microscope, you have a very focused electron beam. It's focused to a very small spot and rastered then across the sample here, indicated by these black arrows. So by this, you get then a very high intensity of the beam on a very small spot on the sample. What's important later on, you will see then that this very high intense beam can also damage the sample. And to control this, it's very important. So the imaging is then performed by scanning the beam over the sample, and the directly transmitted beam is then detected by the bright field detector here. And the scattered electrons scattered on the higher angles are then collected by the dark field detectors, and depending on the angle here, you call it high angle annular dark field detection when you have angles larger than something like 50 milliradians, and conventional ADF when you have smaller angles. So due to the scattering mechanisms, the high angle annular dark field detector is sensitive to the set contrast of your sample. So that means this gives you these very nice atomic resolved maps where you can nicely see heavier and lighter elements as shown by Max before with the manganese and the rare earth metals. So the beam, of course, excites also characteristic X-rays in the sample. And these X-rays can be used to make also elemental analysis. However, they are ejected in all directions, and you can only collect a quite small number of them by an EDS detector. So typically only about 10% are detected, and most of them are lost in the instrument. There are some special instruments made for EDS where you can collect up to 30-35% of the X-rays, because when you place several detectors around the sample, you can, of course, collect more, but it will always be the case that you lose many of them. So therefore, you can also apply the somewhat complementary technique, so the so-called energy loss of the primary beam. So when the beam is transmitted to the sample, it will lose some of its energy by inelastic processes, and this is then somewhat complementary to the EDS. And yeah, the big advantage here is that the central beam, so the directly transmitted beam here, contains about 99% of the signal, and you can collect it to almost 100% with your spectrometer. And that means you expect here in the EELS a much better signal to noise and signal to background ratio compared to the EDS. And especially if you have thin samples and a weak signal, this is always the best method. So to do so, you must remove the bright field detector, yeah, and the imaging still is then performed by the dark field detector. And that's the reason why, in combination with the EELS technique, you always get dark field images and usually no bright field images at the same time. So it's always important that you select the setup in a way that the camera length, so the distance between the sample and the spectrometer opening aperture here matches with the expected scattering angle, because when an electron loses some of its energy, of course, you must take into account the conservation of energy and momentum. You expect an electron to be scattered under a certain angle, and this angle is luckily quite small. And we have used here a collection angle of about 74 milliradians, and therefore we expect all of the signal to be collected in the spectrometer, because typical scattering, a typical angle under that an electron is scattered, a 200 keV electron that has lost something like 1000 eV, what's expected for the rare earth metals approximately is scattered under an angle of about 10 milliradians. And so with these 74, we are absolutely sure that we collect all of them and don't lose signal. So let's have a closer look at the EELS setup now. So the EELS spectrometer is shown here in more detail. Basically, it's made out of a magnetic prism that spreads the beam into its energy, like an optical prism. And these dispersive properties are used to generate finally energy spectrum. And in combination with some optical elements here behind the prism, you can then project this spectrum on a screen or on a camera. Depending on the settings here and on the equipment you have, you can operate it in the pure spectrometer mode, that you just get a spectrum here. And if you're lucky and you have some imaging filters, so some more optics here, then you can also filter a full TEM image and project it on your camera. But this is not what we have here and what we used. We used just a pure spectrometer. You see that this setup is quite complex and quite sensitive to external disturbances. So that means, in general, when you are performing EELS, you always have a little bit of movement of the spectrum in the energy dispersive plane here on the camera. It's never perfectly constant. and it requires more or less permanent tuning of these alignment optics, and also yeah, it's always a little bit unstable in the range of a few, let's say half of an eV or 1 eV. It's always a little bit unstable, and therefore we are using the so-called dual EELS mode. So in the dual EELS mode, you record actually always the low loss region where you have the zero loss peak and the high loss region, so the region with your elements or with the edges you are interested in at the same time. And then by a post-processing step, you can correct for the 0 point of the spectrum of the energy scale and get by this way high quality data. So let's think about the sample again. So a conventional sample, so that means a non-high entropy sample, is usually made out of so if it's a crystalline sample, you have then yeah, the atoms arranged in a very periodic pattern here, and when the electron beam is transmitted here through the sample, as indicated by this greenish arrow, then yeah, it hits many atoms of the same kind, and you will expect a quite strong signal in yeah, all kinds of techniques. In the EDS, you get a strong signal. In EELS, you also expect a very strong signal. But in the case of the high entropy sample, it's then of course different, because here you have different atoms on the sides. And if you have then a, let's say, quite thick sample and you pass the beam through the sample on one atomic column, you get also here more or less all elements, but with a weaker signal, because you have less number of atoms of every kind. And therefore, to get then to visualize the high entropy nature of your sample, you must go to a thinner sample. So you must make it as thin as possible, because when you make it thin enough, then you see that you get then some atomic columns here where one kind of atoms is dominating or some kind of atoms are absent. And yeah, if the sample is high entropy natured, you would then expect here some kind of yeah, colorful maps at the end with an inhomogeneous distribution of the of your elements. So to get such thin samples, you can use, for example, a focused ion beam preparation, as we applied for our samples. And to get a real high quality ultra thin sample without any kind of amorphous layers on top and bottom, you must go down with the energy of your beam. And finally, we polished our sample with 1 kV ions at the end to get yeah, the best out of it. So the question is now, how thick is our sample? Are we in this range that we can expect? Yeah, inhomogeneous distribution of the elements. Luckily, the thickness information is contained in the low loss region of such an EELS spectrum, and you can get it yeah, quite easy by looking at the intensity in the zero loss peak, so the electrons that have not seen any inelastic scattering in the sample, they are directly transmitted, and the rest of the spectrum. And basically, the rest of the spectrum, you find all inelastic scattered electrons, and in combination with the inelastic mean free pairs of the sample, this gives you then the thickness. And what you see here, so this is a real spectrum here from this mapped region of our sample. And you see that, yeah, the plasmon peak, that's always a good indicator of the thickness. So it's very, very weak here. And the this ratio, the thickness of a lambda ratio is in our case 0.09. And yeah, to get the absolute value, you can use the log ratio method. So this is given here, this formula. So you need the negative logarithm of the intensity in the zero loss peak and the total intensity of the spectrum. So you can just get these values by integrating over the intensity here in the spectrum. And you must then also know the lambdas, or the mean free pairs of inelastic scattering for electrons in your sample. And this basically depends on the effective set value of your sample. And also, of course, on the electron energy and some more parameters, but most important, so the only changing parameter is always the effective set of your sample. So the task is now to calculate the effective set of this compound. You can do it in actually two ways. You can just use the arithmetic average. That's the not so precise but very quick method. So there you end up with something like 21. But the more precise way, especially that takes into account the weighting of heavier elements in compounds. And you see we have here light elements like oxygen, but also heavy elements like the rare earth metals and some in between. We did it in this way. And yeah, by applying this formula and then used the formalism implemented in digital micrograph based on the Malus formula, we end up with a lambda of 75 nanometers. And yeah, remember our ratio here, the T over lambda was 0.09 for this case. We get then finally here a thickness at this region of the sample of about 6.7 nanometer. And this is quite impressive. And yeah, this should end up then with the option that we get inhomogeneous distribution of the rare earth metals when performing EELS. So let's go on with this value here again to some structure. So I made here a model of our sample with the specific structure we expect with a thickness of about 7 nanometers. And I filled it then randomly with 5 different atoms. So here indicated by 5 different colors. In between the manganese host lattice given here by the red atoms. And we have a viewing direction in our case of the -110. So that means we get approximately, or we get this arrangement of atoms here. When you then look here at, for example, one specific column, you see, for example, here this column, the pink atom is absent. The green one dominates. So that means for this column, when the beam is here, you would expect that one atom is missing and the green one is dominating, and the others are also present, but not dominating maybe. You can do this then for all columns here in this simple model. You can count in just the number of atoms here, and you will find that in every column, so here the pink one dominates, here the green one dominates, here the gray dominates. In some columns, you get maybe an average, all atoms are present, but in general, you expect some inhomogeneous distribution resulting in hopefully quite colorful maps. So the question is now, is this measurable? So you have a quite weak signal because the sample is very thin. And to get a good signal, we have actually 3 options. So first of all, of course, you can use a high beam intensity, but this might destroy the sample, as we will also see later, that if the beam intensity is too high, you get you destroy your sample. You can also use a quite long integration time to get enough signal, but then you get in the problem with the sample drift. And since we have a perfect lattice there and the dark field detector that can be used to track the sample sees only the lattice, but of course it doesn't see the different, so the elemental distribution. So that means it will track maybe the periodic lattice, but maybe not at the same place, but it will jump from one unit cell to the next unit cell, and therefore the tracking is quite hard. Another option is also to sum up over multiple frames with tracking from frame to frame, if you have some features on the sample that you can track. But since the lattice is periodic, we will see later, it's possible when you go to very, very short pixel times and very fast acquisition of the data with direct electron counting systems, then you can do this, because then the drift between the frames is less than one unit cell, and then the software can lock on a specific place and stay there, and you can accumulate many, many frames. So let's start with our first attempt, or actually it's not the first attempt, but the first measurement after optimizing the parameters that I can show you. So we used a CS-corrected neo-arm instrument with a cold field emission gun, beam energy was 200 kiloelectron volts, and we just used the Gatan continuum spectrometer S. And we did a so-called one-shot measurement, so a single scan, no drift correction, dual EELS mode with 2.5 microseconds for the low loss region and 25 milliseconds per pixel for the high loss region. So that means the total map generated by the settings. So we mapped here this region. It's 44 by 44 pixels, and it takes something like 40-45 seconds approximately. So on the left side, you see then here the dark field image and the region where we performed our mapping. On the right side, you see the sum spectra, so summed up over the full region here. And as expected, we have the zero loss and a very low plasmon peak here. And in the high loss region, we see the manganese signal here. So the manganese L lines from the host lattice and some rare earth metals, lanthanum, neodymium, samarium, and gadolinium. The yttria was not collected because the energy loss is at much higher values, so we couldn't get this in the same spectrum. But we will see later on. We have seen on different measurements that it's also present, of course. So now you're for sure interested in the intensity of a single spectrum here. So when you go to a single spot, for example, on the B side here, where you have a rare earth metal, then the spectrum looks like this. So of course it's quite noisy, but at this place you see the samarium is here maybe dominating. Same is true when you go to the A side where the manganese is placed here. So the manganese shows then, of course, a pure manganese signal, and the rare earth metals are absent here. You don't see them. And yeah, from these signals, you can then generate the maps. So I guess you are all familiar with the spectrum imaging evaluation in the EELS mode. So usually you define some region before your signal for the background subtraction, so indicated here in red. So this red region is used to extrapolate the background, and then you define some green region for the signal, and this signal then finally included here in this peak, or here for the manganese, and this manganese peaks is then used to generate a intensity map or a grayscale map where you get the elemental concentration there. So this is done here for this region. So as an example here for the manganese and for the gadolinium, no, it's the samarium map. And you see the manganese as expected, it shows a quite periodic lattice. So since this is the host lattice, and the rare earth metals, so the samarium here is only present at specific atomic positions, but there are places where you don't get any signals from it. And so, yeah, by the way, this is raw data, raw signal. So it's not, there's no filter applied or nothing. It's really the raw data you get out of the instrument. Please also note here the drift in the manganese lattice. You see nicely that the picture is a little bit drifted during the measurement at the second half of the map. But I said it's raw data, no drift correction was applied. So I think it's, still quite impressive what you get here. And yeah, then we get here, of course, now to the full map we recorded at this place. So final result looks then like this. You see nicely that the rare earth metals, so the neodymium, lanthanum, gadolinium, and samarium are distributed inhomogeneously. So you get places without these elements, and you get atomic columns where you have more of them. And of course, when you integrate over all of them, you finally get then full lattice again. Manganese is, of course, here nicely present everywhere. And yeah, when you then overlay all of them, you get this nice colorful mixed map here. To make this overlay, I must say I applied some filters. So I did a little bit of sharpening and increasing the contrast to get then this nice overlay. But all the other data here are raw data, just colored here to distinguish between the different elements. So now the question is here, is this elemental distribution stable, or is it maybe affected by the electron beam, since we applied a quite high intensity here? And yeah, since we couldn't apply any kind of drift correction here, and also when you repeat the measurement, you're never sure whether you end up at the same place or maybe a few lattice sites off. We couldn't prove this in this way. And also, when you scan for a longer time at the same place, then you see actually that the sample starts to decompose and to get destroyed. So to shed more light on this sample destruction or the stability of the sample during these maps, we were luckily invited from Gatan to go to the lab of Professor Willinger in the Technical University of Munich with a DigiScan 3 system and latest direct electron counting systems to record dose-fractionated multiple frame acquisition technique to get some time-resolved mappings of this sample to see whether this is stable and to confirm our result. So this we can see here. So now this is, let's say, different. So the exposure time is here much lower. The probe current was set here to 26 picoamps, and yeah, time-resolved multipass counted dual EELS experiment was performed. So that means instead of a long exposure time and only one shot, here the exposure time was reduced. This is possible by using the direct detection counting cameras. And yeah, as already said, the experiments were here performed together with Saleh here from Gatan at the TU Munich at the in the lab of Mark Willinger. This is actually a non-operation corrected geol instrument, also an FT100 instrument, but no CS correction applied. And Gatan Continuum GIF is attached to this. So each scan, each image here takes about 4.5 seconds to record. So remember, my measurement took something like 45 seconds. Here, every image is just 4.5 seconds. So that means by adding up, you get then also finally a good result. But you have to add up several images to get enough signal. But in between all these frames, you can apply a continuous drift correction. So this compensates then finally for the drift between the passes. So again, here on the left side, you see the dark field image with subpixel scanning to get this super resolution image used for drift correction. And on the right side, on the top here, you see the relative thickness map, also time resolved. And yeah, what's particularly interesting here is that you can clearly see here the beam damage over the time. So that means that the thickness map, you see the colors are changing here. So when it starts, I guess at 0, you see the black and blue region is quite small, but with time this gets larger and larger. So it gets thinner and thinner here, meaning that actually the sample is burned away here and you get significant sample damage. So here, yeah, since the probe current is 26 picoamps, you see that after something like 10 seconds, there is a significant beam damage. And this corresponds in this case to about 25,000 electrons per angstrom squared on the sample, which causes the beam damage at this dose. And yeah, after the acquisition then continues, the effect becomes more and more pronounced. And after 200 passes, then this corresponds to something like 500,000 electrons per angstrom squared. You have then a heavily degraded sample. So this example, yeah, highlights the importance that you have this power of the time resolved counted acquisition and the dose and beam damage here at the same time, and you can actually have a look at this in situ. So to get rid of this beam damage or to minimize it, we did a second experiment with an even lower probe current. So we went then here to a probe current of 15 picoamps and again performed a dual EELS experiment at the same instrument. And the result you can see here. So on the left, you again see the dark field image with the subpixel scanning to get the nice drift correction here. And on the top right, again, you have the relative thickness map. And here you see then that actually the conditions are stable. So you don't see a significant change in the thickness of your sample. And so one image, so one pass here, one record is then here less than 1 second. That means even a lower dose was applied here with a lower probe current and even a shorter exposure time here, these 110 microseconds. And yeah, even after 700 passes, the total dose is then something like 700,000 electrons per square angstrom, but you don't see any significant beam damage. That means the total dose is higher, but it's distributed over more frames, and therefore the beam damage can be reduced there. So yeah, when you look more closely on the relative thickness map, you see the variations here are in the third decimal place here, of the relative thickness, and therefore you can actually say there is no significant damage. So that's a very strong contrast to the previous experiment. So where you have this clear beam damage, beam-induced damage. Even after 10 passes, here we recorded 700 passes, and there is actually no significant damage. And that means that it's not only the dose rate, not only the total dose that is important, but the dose rate is important to avoid beam damage in these radiation-sensitive systems. So of course, you want also to see the maps now here from these measurements. So here in this slide, you see then the results, the atomic maps. It's quite impressive that you still get such high resolution mappings here, and this drift correction worked quite well. This is a sum then, a sum of all the high quality drift corrected scans. And yeah, finally, we end up here also with atomic resolution EELS maps at a non-aberration corrected instrument. You can clearly see the atomic lattice here on the manganese map, and importantly also for the different cations like the samarium, neodymium, lanthanum, and so on. You see also here an inhomogeneous distribution of this rare earth metals, and especially when you look at the samarium and neodymium, you also see the atomic positions. It's not so clear, of course, but you can nicely see them, and they are locally resolvable and clearly correlated. So yeah, at the same time, the host lattice stays here intact. That's quite also important. And this result is then consistent with the stationary random and locally resolvable cation distribution expected for these high entropy solid materials that we have as a sample here. So now when we not sum up all the 700 frames we recorded, but maybe just focus on the first 100 drift corrected passes, then of course the beam damage is even lower. Well, there is no beam damage, but to be sure that this gives the same result when you just record the first 100 frames, you also are able then to see the atomic resolved map here in case of the manganese, and also the heavy atoms here. And this is still quite impressive compared to the first slide here, where it's summed over 700 frames. That also the first 100 frames give you a quite nice signal. So this is only possible, and that's a big key advantage here, that we have this fast acquisition enabled by the direct electron counting detector with very short exposure times of 110 microseconds, and this significantly reduces the interaction time between the beam and the sample, and therefore reduces the beam damage. And this fast acquisition is beneficial in two ways. So first, you have a very good option for the drift correction between the frames, so the individual passes are acquired quickly and can precisely be aligned. And second, this very short dwell time reduces then the beam damage, as mentioned before, and you don't have the beam on a specific place for a long time. And another important point is what should be mentioned, that these direct detection counting cameras can be easily used to sum up the individual passes, and by summing up you will not get some additional noise. So that means there's no penalty for frame summation in this direct count dual EELS mode here. And yeah, this allows them to acquire the data rapidly and accumulate the signal by summing up passes actually as long as you want. And you can, even then in a post-processing step, check the first 100 frames as shown here, or also all frames, look at the development of the sample during your measurement. Yeah, so with this, I'm at the end of the talk. And I want to thank especially Gatan, especially Saleh and Ray and Jonathan to provide me here this opportunity to make this webinar together with Max. And of course, special thanks goes to the Technical University of Munich, to Professor Mark Willinger, to give us the option to measure it in his lab with this latest instruments. And of course, the DFG, I also have to thank them for funding of the ELMICO, of the Electron Microscopy Center here at the University of Augsburg. That's the funding number, because without this, we wouldn't be able to do our measurements here in-house. And yeah, whenever you have any questions regarding the equipment or the EELS stuff or whatever, then feel free to contact us here. And yeah, with this, I'm at the end, and I guess I hand over to Gatan again.
Thanks a lot to our speakers. So thank you, Aladdin and Max, for a nice presentation. We have some time for questions, so I'll start going through what has come in. I'll try to avoid repeating similar questions, and if we don't get to your questions today, I will make sure to follow up by email afterward. So let me start with the first question. What is the camera used for EELS on the slide 31? So basically, it's your first data that you showed, and yeah, and what is the pixel time? So I think you have already mentioned that.
Yeah. So the pixel time is so for the EELS, the low loss spectrum recorded was 2.5 microseconds, and the high loss spectrum was 25 milliseconds. And we use the Gatan continuum spectrometer here. Yeah, it's let's say standard continuum spectrometer. So
yeah,
I don't know.
Maybe I also add that this is the system that they have is a Continuum S. It has a scintillator-based camera, so we call it GIF camera. So
yeah, it's not a direct electron counting system, but it's scintillator-based. Yeah.
Exactly, it's a scintillator-based.
And I guess maybe it's important or not. It's a, let's say, modified version that, so the scintillator is capable to count electrons, to collect electrons from 30 kV up to 200 kV. So it's not the standard one, but a little bit modified for us for low kV options. But we applied here 200 kV beam energy, so this doesn't matter actually.
Yeah, great, thanks. The other question is, I think, about the conditions of the microscope, which you mentioned some of them. So the spot size, the C2 aperture.
Yeah, so the spot size, so it's a geol instrument. The spot size was spot 8. Spot 6 or 8. I was not sure about this. I guess it was spot 6 that we used. So a little bit more intense. There's a 40 micrometer condenser aperture, 2 centimeter camera length for the EELS, and a 5 millimeter entrance aperture for this spectrometer.
Okay. The next question is about the time result, or maybe before I go there, I have another question that someone is asking. I think you did mention this, you did talk about the sample preparation, but someone is asking, just wondering how to prepare such a thin TM sample.
Yeah, by focused ion beam. technique and lowering the beam energy down to 1 kilo electron volt. And then it takes some time, of course, and of course, not the first sample was not successful. We burned it away, and it took us, I guess, 2 or 3 samples until we got a good one.
Yeah, so normally it's quite difficult because you also have the straining and the sample is bending.
Yeah.
So to reach that, it's a very impressive sample actually, less than 7 nanometers.
Yeah.
So I guess that's the reason. The other question is, some elements show short range order behavior in the mapping. How can we confirm this is real or artifact? I think
for
you did
example,
talk about it. Not, yeah, I mean, in general, I guess you did talk about short range. Yeah, so I think this probably goes back to what you explained, that what you see, the mixture, because of the mixture of elements and the very thin sample that we have, we do not see all the elements in the map, and some of them are missing, which what you nicely explained. Yeah, I think that's the main reason there. The other question is about what is the pixel time for the time resolved counted dual EELS? So this is the last set of data that you showed. Maybe you did mention that this is also it's written here that is 110 microsecond. So this is maybe I can also answer this. So this is the 110 microsecond for low loss and 110 microsecond for high loss. So in total 220 microsecond for the summation of both.
Yeah, but it's microseconds, and the method I got it here. Our instrument was 25 milliseconds, so that's a big difference.
Exactly, it's a lot more. The other thing is that here we have used subpixel scanning, and that means instead of the beam staying at the center of this 1 angstrom pixel, it's divided. In this case, we have chosen 4 by 4, so you have 16 pixels. So then you can divide that by 16, and it gives you around, I think, 13 microsecond subpixel dwell time. Yeah, good. And this is the key here, because first of all, we get a very nice super resolution ADF image, and that is used for the continuous drift correction. So the drift correction is basically continuous, meaning that it's not going back and forth to another region. It's doing a drift correction from the same area that you are acquiring the data.
Yeah. And since I guess the frame takes about 1 second to record, so within this 1 second, the sample is moving less than 1 atomic 1 unit cell here, and therefore you can then lock at this place, and you don't go from one to the next side and move around.
Yeah,
and that's only possible with this very low pixel times and very fast acquisition.
Exactly. And the other question was, did you sum the first 100 passes counted EELS in GMS? Yes. So when you do, so I think we do have some videos actually showing how to do this, but because we have this time resolved data set, you can basically have access to all the passes, so all the 700 passes. And then you can decide, you can treat it similar to the way you treat actual in situ data. And you can sum, for example, the first 100 passes. The other question, let me see. Able to draw. Yeah, so I think this is similar. Yes, so it's a question about the motivation of doing a multipass to see that the positions of different atomic species were stable or constant. Can you comment on whether you were able to draw conclusions? So yeah, what the conclusion, I think you did mention, right? Maybe
Yeah.
you want to comment on that?
So yeah, when you see the total sum of the 700 maps and compared to the first 100 counts, then frames, then you see actually, when you, for example, look at the gadolinium, you see here obviously on the left side some darker region, and this is also present here for the first 100 frames. So that means obviously this is not changing significantly. Also, the lanthanum here, you see the dark region here clearly pronounced, of course, for the 700 frames. It's also present here for the 100. So it's actually the same structure, but of course a little bit more noisy. But you don't get a change here in the composition when you look at the different frame sets here. So what we have not done yet is to evaluate the first 100, the next 100, the next 100 to see this. But I guess this we can also do soon, and but it will confirm this, because when it doesn't change from 100 to 700, just contrast and noise level is getting better. Yeah, it confirms the stability, and also the thickness map confirms that there is no significant degradation of the sample.
Okay.
Yeah.
Yeah.
And I guess that's the important thing, yeah, that you observe the sample quality or the beam damage. You can observe it in situ, and that's maybe more important, and to judge the final data quality and reliability.
Yeah. So the questions keep coming in. Maybe I will end with this question because of time, and then we'll answer the rest over the email. So it says, it looks like you extracted the white lines for the atomic EELS plotting instead of using the quantification in GMS, which avoids using illness region. Is that correct? What if some elements have no white lines, for example, just a flat edge jump?
Yeah.
Do you want to?
You see here, so actually this, the questions, what do you call white lines? So usually for the transition metals, you have these very strong white lines, yeah, like manganese, but also here the heavy elements, the rare earth metals here, they also have quite strong signals.
Yeah. So maybe I can also add that so in GMS you will have many options when you want to do the quantification. Here, of course, we do have white lines. We have some models, but one thing that is also very powerful is that you can create standards, and with that, that can significantly improve your quantification result. The other thing that we did here, so that means that even if you do not have white lines, you still have some ways to create your own standards. Although the models, the hardest latent model that usually we use, which many times works, but especially if you have overlapping signals or very close, or signal or edges that are very close, then you can use the standards to nicely differentiate those. So even if you have an edge which does not have any white lines, then you are still able to do that. And we have done this. We have many examples. The last thing I want to say here is that we actually did the result that you saw the maps on the last slides. They counted were areal density. So this is a quantitative result. So we're because we do acquire data, we use dual EELS. We can have the low loss to remove the thickness effect, and we get the atoms per unit area. So this is what you saw, but there are many ways to make sure that you are able to do the maps even for the edges where we do not have very sharp onset, like M edges and N edges.
So
yeah.
Sorry to interrupt you. I see that there's some timer counting down here in the webinar software.
Yes.
I have here.
Yes. Okay, yeah. So no, I
It's
think
more than
for the
15
sake
seconds.
of time, yeah, for the sake of time, I will stop here. And so for those questions we did not get to, we'll follow up and respond by email. So you should expect to hear from us. Thanks again to Aladdin and Max for sharing their nice results. And thanks to everyone for joining and for the questions.
Thank you.
Thank you.